let me first start with the actual material, because we are in the middle of cosmology. I didn't finish that part last time. Remember last time we discussed gravitational waves, which is actually an exciting topic, because with the detection of gravitational waves, which has now become possible, we have in a way a new window into space. We can now not only look at radiation or light, but we can also look at a completely different thing, namely gravitation directly. Then towards the end of last lecture, I went on and told you about what is maybe called the standard model of cosmology, or could be called like that. And this standard model is based on the assumption that space is homogeneous spatially. I mean, not in time, but in space, like direction, it's homogeneous, and it's isotropic. And I will briefly explain this model, or mostly its consequences, at the beginning of today, I mean now, and then I will move on to the information loss paradox. Okay, so I think last time I already mentioned that if we assume that we have these symmetries, which is of course an enormous simplification. It's as if we look at the whole universe, all matter that is inside it, but also the geometry itself as just an enormously large gas. But we are not looking in a more fine-grained way, so we don't see individual galaxies or whatever. So there are no objects. Everything is just a big mass, a big mess maybe. And then we saw that the metric must, just because of these assumed symmetries, have the form that it looks like this. So maybe I'll draw here some helping lines. This part is itself a 3×3 part. It's a spatial part. And so the claim there is a metric in the coordinate system, an appropriate one, such that we can, such that the components are given in this form, which means in particular we have no off-diagonal terms between time and space, and we have only a time dependence here in a scale factor. So A is a scale factor. I mean, what that means, it's for the moment, it's just that it's some real number that depends on time in general. Of course, it shouldn't depend on space because we are homogeneous in space. And this other thing here is, again, an isotropic and homogeneous metric on just space, which is constant, independent of time and space. So all the time dependence is captured by the scale factor here in front. That somehow makes sense intuitively, because if we assume these symmetries, then all the parts of the universe have somehow to scale in the same way. It cannot be that they scale in different ways. That would violate the assumption. We haven't actually derived that this is the unique form, but one can show based on the assumptions of these Killing vector fields that I mentioned last time, which formalize spatial homogeneity and isotropy, one can show that it has this form. And this gamma, there's only kind of a few choices left. Either it can just be flat space, or space could be like a huge sphere, of course, on a higher dimension. So it would be a three sphere. And usually when we think of spheres, there are two spheres. There are two spheres embedded in three-dimensional space. And with a constant curvature everywhere and in all directions. Or it could be somehow a hyperbolic manifold where you have, in a way, a negative curvature which corresponds to everywhere having saddle points. But for the moment, let's just assume that it's flat there, because that will simplify our considerations. One can repeat everything we do also for metrics here, which are, as I said, spheric or hyperbolic. Let's for the moment assume it's flat. And then I should add a correction. It's actually convention to here, and the useful convention, to put the scale factor here into the square, because of course the metric measures always distances squared. Then we take the square root, and so it's kind of a convenient thing to write the scale factor like that, so that it's really a scaling in distances and not in squares of distances. Okay, so far there is no Einstein equation or so that has been used. That just follows purely from the symmetry. But of course, you can now insert that metric into the Einstein field equation. So the Einstein field equation have, of course, the Einstein tensor. And this tensor, obviously, as you well know, depends, of course, on the metric eventually, the metric and its derivatives and so on. So that's the left-hand side of the Einstein field equation. On the right-hand side, we have, of course, the usual prefactor with the Newtonian constant, and then we have here the energy momentum tensor of the matter in the universe. And for the moment, we will assume that the matter in the universe is a perfect fluid. Maybe you remember a perfect fluid is basically, by assumption, matter that has energy momentum tensor of this form in an appropriate chosen coordinate system. And of course, it's again isotropic and homogeneous. So all these things only depend on time, but not on space. So maybe I could write here rho of t. So the density of the matter could change over time as the universe evolves, and also the pressure, but there are no spatial dependencies here. Now you may wonder, where is the cosmological constant? Because if you are doing cosmology, we should probably include it, because if it has somewhere an effect, then it has one in cosmology. I hope you remember that I said last time that we can include or treat the cosmological constant or the cosmological term in the Einstein field equations as a matter term. And if we do that, then we can just include it in this T with a particular choice of rho and P, namely that rho of T is equal to minus P of T. So this is what I meant when I said last time it has negative pressure. And this is all equal to this constant. So it's therefore independent of T. And a scale and just a normalization factor, another constant. So at the end, this statement is that the cosmological term acts like matter that keeps a constant density in the universe. And that's another remarkable feature of, if you want to think of this really as matter, because it would be matter that is constantly generated when you pull it apart. Because to say that the density remains the same means that if, for example, the universe grows, we will see what that means in a minute, if this scale factor here increases, then the density always remains the same. So it's as if you take some matter, you kind of pull it apart like a chewing gum, but it's always the same amount of density. So it always keeps rebuilding matter so that you never lose anything. So you kind of tear your chewing gum and there's more and more stuff there so that the density at every point is always the same. That's how one should think of this cosmological term. Okay, now you of course know very well how to evaluate Einstein's field equations. You have now done it if you went to the exercises at least for two different cases, namely for the spherically symmetric solutions that led to the Schwarzschild solution of the Einstein field equations, and also the linearized versions, which are treated, actually they will be treated this week. These are the ones that are used, for example, to do the gravitational waves. Now, in this particular case, if you insert this metric here, of course, what you have to do, you have to calculate this Einstein tensor, which is quite straightforward. You just have to determine the gamma symbols and then take derivatives to express the metric in terms of them. And so you get some expression which at the end will involve, of course, the term A and probably derivatives of A and maybe also second derivatives, because remember, the gamma symbols include already first derivatives of G, and the curvature has then again derivatives of the gamma symbols as well as gamma symbols squared. So one can insert that and just calculate, and it's something you could easily verify, but I will not do it now. It will be part certainly of cosmology courses to just write down what these equations mean. And it turns out that the Einstein field equations for this particular choice of the metric for the metric. Actually, I think I mentioned that this is usually called, I mean, this metric has a name. It's a Friedman-Robertson-Walker metric. I think there's also sometimes Lemaitre here. So let me call it FLRW metric. Reduces to only two equations. Recall that the Einstein field equations are in principle 10 equations, because we have, of course, to evaluate them for each choice of these indices up to symmetries, and there are 10 different choices. And now for this particular metric, there are only two independent equations that remain, and they look as follows. I just state them, and I leave it to you to verify them if you like. It's really just a very straightforward exercise. It takes a bit of time to evaluate all these gamma symbols, but there is nothing conceptual that comes into that. So let me call that equation 1. So that's the first, and the second one looks like this. A dot, okay, actually maybe I normalize it. A dot divided by A squared. Oh, no, okay. I think it's still nicer if I write it like that. You know, the curvature term usually also has squares in them. And so it's not unexpected that we will get squares of the derivatives of A. And it turns out it's, again, a quite simple expression like this. And this is, as I mentioned before, for the case where the spatial metric is flat, which if it was a sphere, you would have here an additional small curvature term, which is, however, a constant, because you assume you can, if this curvature would change, it would absorb it into the scale factor A. So let me call that equation 2. So that you could just figure out yourself. They have names, these equations. The first is called the acceleration equation. And the second is called the Friedman equation. And there are more general versions of them, but at least that's one of the special cases of them. Now, of course, I could, or let me introduce something else which is common in this field. People talk about the so-called Hubble parameter. The Hubble parameter is something that depends on t, so it's not a constant. You may think of the Hubble constant, but it's not a constant in time. It's maybe a constant in space, because it doesn't depend on space, but it's not a constant in time. That's something I would like to emphasize. So I could define this and give it this name, Hubble parameter. And then, of course, we can rewrite 2 in a very simple way. We just take the A to the left-hand side, and then we have here the Hubble parameter squared equal to 8 pi over 3 Gn times rho. Okay, that's just a different way to write 2. Now let's see what these equations tell us. And this is now the interesting part. And I will just essentially make one example and maybe mention a second. Let's assume the universe had no matter in it, or the matter was so small that we can neglect it. This is actually not an unreasonable assumption, because I told you last time that the cosmological term, if you regard it as matter, and now, of course, we don't want to neglect that term. So when I said we neglect matter, I meant we neglect all matter except for the matter that, or let's say the treatment of the cosmological term as matter. And I mentioned last time that the largest fraction of the stuff there in the universe is actually dark energy, which is exactly the stuff that comes from the cosmological term. So let's just assume that this is all the stuff we have in the universe, and let's see whether we can find a solution to these equations. So if no matter, but only I should say real matter. I mean, by real, it includes dark matter, but not the cosmological term, but only cosmological term. the equations become extremely simple. Okay, to see that, let's just insert things. So what we have to do here is to realize that rho plus 3p just gives basically minus 2 rho, because p is equal to minus rho. So this bracket is minus 2 rho. But rho, we have an explicit expression for rho. It's just lambda over 8 pi gn. So it essentially just cancels here. And we have this 2 here. So this 8 really cancels everything here except for the 3 here that remains. The sign will also be cancelled because we had this minus 2 rho coming from this term. So what we get is that the first equation, the acceleration equation, just turns into the equation that a dot dot is equal to lambda divided by 3 times a. By the way, I forgot to mention, but it's probably clear to you that when I write a dot, I mean the derivative with respect to time. In this case, there's no proper time. We are not talking about a particular object. So here we really just mean the time, which is defined as the first or the zeroth coordinate according to the coordinate system we chose, which is a coordinate system in which this looks like this. So this is the coordinate system with respect to which space looks homogeneous. Maybe I should let's say, remark that if you move, so let's suppose you have one coordinate system with respect to which the metric looks like this. And this means you have an observer with respect to which we have essentially a complete symmetry. But now if someone moves very fast or just moves with respect to this observer, we would have to Lorentz transform, even if it moves uniformly, this metric with respect to that velocity, and we would get off-diagonal terms. So it's not true that for any observer it would look isotropic, for example. So the isotropy is kind of an observer-dependent notion. So the claim is really there exists an observer or a coordinate system, formally speaking, such that the metric looks like that. This is just to remind you what this actually means. And so therefore, these derivatives in time are with respect to that observer. It's kind of the time of that observer, of the coordinate system of that observer. Now the second equation, I'll just take it from here, which is already a rewriting of the second equation, turns into a dot divided by a, that's the Hubble parameter, is equal to also lambda over 3. You see that very easily. You just see that rho, if I again insert for rho this expression here, I just cancel everything except the lambda over 3. And now if you look at these equations, you can probably very easily see, or at the end verify, that a possible solution, let me even give the general solution, I put here an arbitrary constant, is just this one. So I mean, just insert this here, and you will see that in both cases you just get lambda over 3 out as a prefactor. So what does this mean? It means under our assumption that that there's no other matter, the scale factor grows exponentially in time. Now that's just a factor that we introduced in a metric, a purely mathematically defined object. As always, we are interested in the physics of this whole thing. So let's explore what that means. And remember, we did the same thing for gravitational waves. A priori, if you have just a wave expressed in terms of certain coordinates, it doesn't mean that this is something you can actually measure. It could just be that you actually chose coordinates which kind of wobble around, but space would just always remain the same over time. That could be, and then the equations would look as if you had a wave, but there would not be a real wave. So it's always good to verify that we can actually observe things, or that what we calculated corresponds to something that is observable in principle. Only then can we be somewhat, or become excited and say, oh, this really means something. Of course, this suggests somehow the universe expands, but we are not there yet. So we'll make a similar picture as last time. Let's suppose in the coordinates that we chose, there's this x1 and there's x0, which is equal to t, according to our convention. We have here, let's say, Earth, that's us. So we choose the coordinate system such that it's at 0. And then at some coordinate distance chi, so this is just some value, we have a star, let's say. Now let's suppose that both Earth and the star are moving upwards, which is actually the only possible choice with respect to which things remain isotropic. So of course, if I assume the universe is isotropic, it doesn't make sense that the star moves like this or like this, because that would break the isotropy, because if I now rotate the whole thing, it would turn. So the only isotropic way to place matter into this whole thing is to consider a situation where in these coordinate systems, things just move straight up in time, but don't move in space. Now, I will not fully repeat the calculation, but of course, you know from the analogous consideration we did for gravitational waves, or in the context of gravitational waves, that if we plot these straight lines, this doesn't mean a priori they are geodesics. But let's briefly go back to our metric. So see, this metric has a very nice form. It has, for example, here, no off-diagonal terms. And also it is true that, for example, this term is just a constant. So it doesn't, in particular, it doesn't depend on time or on space. So what does this imply? Let's see whether the green line, the green world line and the blue world line are really geodesics. And how can we do that? We do it in the same way as last time. We just write down the geodesic equation, which we can reduce to the case where we only move in the 0 direction. So we take the geodesic equation for the special case where we start our movement just upward. So we have only a gamma 0 dot component and all the other components are 0. And then the geodesic equation looks like this. Now, last time we calculated this. Actually, it's something I could even write down because it's so brief. Remember that for the Levi-Civita connection, the explicit expression for the gamma symbols looks like this. But you can easily verify that all these terms are 0, because remember there were, we only look at I equal 1, 2, 3. So we want to see whether there is a deviation in space, whether suddenly these geodesics start to move in space, which would anyway be strange intuitively because we assume isotropy. So that would already be an argument, but we could also verify it like this, because there is no off-diagonal term in the metric, and also the 0, 0 term has no dependence on space. And you see here from this Gij, I and J, if I is a space-type coordinate, J also has to be a space-type coordinate. So this just shows that we can essentially neglect this term, and we get our conclusion that the geodesic in these using this metric is just a straight line in the coordinate system. So in other words, if we really place just Earth in the universe and a star somewhere else, and they just are free falling, which is what the geodesic means, and which they are doing, then this is the correct description in these coordinates. Now, like before, like for the gravitational waves, in the case of gravitational waves, remember this was one, let's say, point of the detector, and this was the end of the arm of the detector, and we measured distances. We can, of course, also measure the distance between us and the star. So some distance, which I call dE. Okay, let's call the star just S. So then I call the distance DES. And this distance may depend on time. Obviously, obviously this is not obvious from the diagram, but you know the metric depends on time, and therefore we have to expect that also all the distances in our diagrams depend on time. Of course, to measure it, we would have to send light or receive light, and light would, of course, travel like this. So if the metric changes over time, this would have an impact on the light as it travels. But let's, for simplicity, assume that this is a relatively close star, so that during the time when the light from the star travels to us, the metric doesn't change substantially. So this is only true if you look at some object that is close, and I will later give you some numbers of how close that would need to be, or how fast these things change. Okay, so what's that distance? So let's just calculate the distance using the metric. The distance between E and the star, the Earth and the star, is just given by as follows. So normally, in order to evaluate the metric, you would have to integrate along the path from here to here. But of course, the metric stays spatially or is independent of the space, of the spatial coordinate. So instead of integrating, we can just multiply with the spatial coordinate, which is chi, times the value of the metric. So G 1, 1, as we go in the one direction. And because of our sign convention, there has to be a minus, and there's also a square root because we talk about distances. So that you should probably easily now see, given all your knowledge about differential geometry, that if I have a metric with this component, then if something has coordinate distance chi, then the real distance is just given by chi times the square root of the corresponding component. And as I said, the sign is just there because it's a spatial distance, and the signs are chosen such that time-like distances are positive. But here we are really interested in the spatial distance. And what does this give us? It gives us chi times, and now we have to read out this component. So the 1, 1 component is minus AT squared times gamma 1, 1. So let me just write this. It's A, and then the square goes away because of the square root, and then we have the gamma 1, 1. But the gamma 1, 1 is a constant. That is not time dependent by assumption. All the time dependence is absorbed by the A term. Now, another thing I could do is to take the derivative, the time derivative of the distance. And okay, that's pretty simple to do. What I get, obviously, just from the expression here is that I get chi times A dot t, and the constants remain the same. And the reason I'm writing this down is that, of course, this now gives us an expression for what I call the Hubble parameter, which is A dot divided by A, because you see, we have the only difference between these two expressions is the A and the A dot. So if I divide the two by each other, what remains is really the D dot, the Earth star distance, and the D Earth star distance. So what does this mean? It means that there's this Hubble parameter, and this Hubble parameter is essentially giving us the ratio between how fast the object moves away from us. So first of all, this term tells us things are moving away from us. This is a non-zero term if AT is non-zero, and actually it's exponentially moving away. And the rate at which it moves away is given by this expression. Okay, so the conclusion from this calculation is that we can really interpret the scale factor, the A factor, as a measure for how fast the universe somehow grows, in the sense that objects that are away move away. But the further they are away, the faster they also move away. Let me just, what I mean by that is I can of course write it like that, h times dEO. So this just tells me if I know the distance of an object at a certain time. And the Hubble parameter is a constant over space. So if I look at a particular time and I know the distance of an object, then I can also immediately determine the velocity by which it moves away, or vice versa. And of course, the opposite direction is interesting, because the velocity by which it moves away has an impact on the frequencies we observe. There will be a redshift. If an object moves away, we can determine the velocity by which it moves away by just measuring its redshift. And so therefore, by taking this and dividing by the Hubble parameter, we can get the distance of the object. So that means that the redshift of an object is directly related to its distance in this model. Of course, this model has all these assumptions about homogeneity and so on, but on a very large scale, that's supposed to be a good approximation of what's going on. Okay, let me just mention a few conclusions of that. So I think the most interesting conclusion is that space really grows. So in some way you could think, I mean, how can it be that the distance here grows? It's really that constantly there is new space created in between any object. And that's true for any object. So you can take any object as a center. That's of course now an Earth-based view, but Earth is not special. I could go to any other place, and wherever I am, it looks as things move away. So the universe grows locally. And people actually managed to measure how fast this is. And they found out that, I mean, this is of course given by this Hubble parameter, and the Hubble parameter has been measured, among others, with the Hubble telescope that you may have heard of. And the answer is of the order of a few centimeters per second per light year. So what does this mean? It means that if I observe an object which is 1 light year away, then this object roughly moves away from me with a few centimeters per second. So that's pretty slow velocity. So I look at an object that is very far away, and this object moves away, but only due to the space that is created in between me and the object. So in between me and the object, there's a little bit of space being created all the time here. And the net effect of that is that if the object is a light year away, this moves by this very slow speed of just maybe 1 or 2 centimeters per second. The other consequence is by the way, that the distance here, or this velocity, may in principle be larger than light. So if this object, this blue one, is really far away, then this distance will grow at the speed faster than light. This is not in contradiction to anything. It's only, I mean, I'm here and this object moves somewhere here and I cannot directly see it. So it's not that I see something moving faster than the speed of light. It's just that space is generated so fast, or there's so much space created in between because the object is so far away, that the net velocity by which it moves away is so large that it exceeds the speed of light, which means, of course, that if this object sends out a light signal, it will never reach me. The space that is generated in between will just be larger. And so there is a bound on the observable universe. That's the other consequence, that the observable universe is bounded by, I just take this expression, put here C, and then I mean, this is one of the opportunities where I really write the constant C divided by H. So that's just from this. So there's only a certain part of the universe we can actually observe, and the part changes its size, because we have calculated that there is this dependence here. I mean, if there was only the cosmological constant, the Hubble constant would also be constant, but of course there is also matter, and this has also an impact. The final, very final thing just to mention, I could also solve the Friedmann equation and the acceleration equation that I stated here for the case of matter. So solve 1 and 2, for example, for dust, let's say. For dust, P is equal to 0. And again, I'll just state the solutions. The solutions will be that rho will be proportional to a to the minus 3 of t, and a of t will be proportional to t to the 2/3. So this will be a universe where there is mostly dust or some other matter. And you will find these two solutions, which I can, of course, combine. And if I combine them, I get a remarkable result. I get the result that rho of t will be proportional to t to the minus 2. Why is this remarkable? It means that if I go back to time 0 in the coordinate system, the matter density will diverge. And that's essentially the cosmological reasoning for why there is a Big Bang. So you see, there are all these interesting cosmological facts that one can derive from Einstein's field equations. As I said, the idea here was just to give you an overview. Maybe to summarize, what we had is we said that we make this enormously simplifying assumption that the universe is just essentially a big gas. And then from this assumption, inserting the resulting metric, which reflects this assumption into the Einstein equations, and making and just solving it for particular cases, for example, where we look at mostly the cosmological constant, or we look at matter, we get very interesting things. We get, for example, that the universe has to accelerate in an expanded way. And we also get the idea that if matter was the dominant factor, then the universe has somehow a starting point. And this starting point, by the way, is just the inverse of the Hubble constant. You can see that probably just from the equations. So remember that here, when you look at the equation that we had, then a dot, or maybe I'll look at this version here. Where is it? Okay. I think it's okay to have this version, that a dot divided by a squared. Oh, sorry, I think I made, there was a square missing. Of course, this only makes sense if I have an a square. So please correct that. There was an a squared, because of course I can take this on this side and then it gives that thing squared. But if you look at this expression, it means that a dot squared divided by a squared, the Hubble constant, is proportional to rho. But if rho is 1 over t squared, this means that the Hubble constant is proportional to 1 over t. So it's really not a constant in time. It should really be called a Hubble parameter, and it's the inverse of the age of the universe. Okay, I hope I could give you a flavor of what would expect you if you decide to take a course on cosmology. In cosmology, of course, one combines these considerations, because of course it's interesting to see what happens in the real universe, where we have matter and the cosmological constant. And what essentially the result will be is that there are different epochs. The early universe is dominated by radiation and then matter, and the late universe is dominated by the cosmological constants. So both behaviors that I showed you now are somehow extreme cases. The second one I mentioned is the early case leading to the Big Bang, and the other case is the one far in the future, when matter is so dilute, real matter, that only the cosmological constant is relevant. Okay, so this concludes this part on cosmology. And yeah, are there any questions about this topic.
There are two questions in the chat.
Yes. Mm-hmm.
So the first one is about the assumption of isotropy,
Mm-hmm.
and whether it somehow can be proved that this assumption doesn't lead to any like incorrect conclusion.
Okay, what could happen is, of course, that if you make too many assumptions that and then go with your metric into the Einstein field equations, that you don't find a solution. And that would show you that the assumption is inconsistent. But in this particular case, this is not the case. So if you just insert them into the Einstein field equations, everything works. Of course, there could be other principles in the universe that are violated. And at the end, we never know whether an assumption is perfectly consistent. But within GR, where we only have the Einstein field equations, that's a perfectly consistent assumption. Another question is, of course, does it really reflect reality? And obviously it does not. If I look in one direction of the universe, it looks different than the other. But the idea is that it's still a good approximation. If I look in a very coarse-grained way, then everywhere there are stars and so on, and everywhere are galaxies. So it's an assumption, and it's a consistent assumption as far as we can tell so far. I mean, probably you know by Gödel's theorem, you can never prove something is consistent, but it doesn't lead to an inconsistency immediately when we insert it into Einstein's field equation. But that's a good question. That's something we always have to check when we make assumptions.
And the second question, I'm not sure if you already answered it by telling about the coordinate time t. But the question is that if here everything only depends on time and not on space, if it somehow defines an absolute time.
Yes, I think the assumption, I mean, that's somehow maybe partially answered by what I said before. I said before that the assumptions single out a particular observer, because as I emphasized, the assumption is that there is this, there are these Killing vector fields, if you remember them, and given these Killing vector fields, it means there exists a coordinate system such that the metric looks like that. Now, a coordinate system is always an observer-dependent choice. So another observer who moves will not find that. I mean, let's suppose an observer takes a coordinate system that is co-moving, which is, of course, the natural choice. Then we could say there exists, therefore, an observer with respect to whom things look like this. But it also means in general that if we now ask another observer, is that really the metric you would see or the metric you would give as a description of the universe, he would say no, because if I transform this metric in general to another observer, there's no reason to believe that I will still get something which has here no off-diagonal terms. I mean, you know very well, for example, that a boost, I mean, just moving to a moving or transforming to a moving observer generally creates here off-diagonal terms. So unless there is a very special choice for this, like if this was just maybe a pure flat metric where AT is not time dependent at all, we would get these off-diagonal terms, which would then mean that for this other observer, things would not look the same. And then we say, okay, for the observer for whom this looks like this, or we take this observer as the observer that defines the cosmological time, which is the time I called t now. So in other words, this t, which you may call cosmological time, is the time with respect to the observer, with respect to which the metric looks like this. I hope this helps, but this is a good thing to remember, that it really singles out one particular thing. So it's kind of a foliation of space-time. It's no longer Lorentz invariant, what we have here. It's a universe where there is really a preferred time direction under this assumption. Okay, if that was, if there are no other questions, then I would now conclude this section, and after the break, start with with the quantum information paradox there, will also only give an overview, but I hope I can at least give you an overview that allows you to understand where the difficulties are and which will answer the question of why is it so challenging to quantize gravity. What are really the problems that we would expect to encounter? But let's first make a break, and because we also have to discuss the exams, I hope you wouldn't mind if we maybe reconvene at 5 to 1 and then discuss a few admin questions as well as questions about the upcoming exam. I will tell you what the idea is of the exam and so on.
I have a question.
Yes, please.
When you introduce the Hubble parameter and brought to the Friedmann equation,
yes,
and we derive another version of the Friedmann equation, right? But I think there should be 1/8 at the new version because yeah.
Oh, so let me see what you're referring to. So are you talking about this page that is now shown?
Yes.
Okay. Yes. We have, okay, what I'm doing is I do this, I have this definition. And so the definition, yeah, here was this mistake, but of course, if I take the A here on the other side, then I get this. So this equation, I guess, is still fine. So you're talking about...
yeah. Oh, if there is a square, then it is fine.
Oh, yes, this was a mistake before, yes. That was, here should be a square, yes.
Yes, thank you.
Was that the problem? Yes. Okay. Are there further questions?
I have a question about the expansion of space between two stars.
Yes.
If we say imagine there be a solid rod between these two distant celestial objects, holding them together, does this expansion of space then
somehow something here that fixes them?
Exactly.
Yes.
Does this expansion exert a force on
this
solid rod?
It necessarily have to exert the force, because what we mean by a distance is really the distance that would correspond to like how the physics works locally. And if you, for example, think, I mean, that's a very interesting question, because we have to ask then, what does it mean that the distance grows? But if you think of this rope just as, let's say, a bunch of atoms, which it probably is, and there are many atoms close together, then when we say that the metric measures distance, then the metric is chose because the physics, the local physics, has to remain always the same with respect to the metric. So if, for example, an atom, two atoms in a solid, let's say in some, let's instead of a rope take some iron bar, which is really a very solid object. So let's suppose we measure the distance between the atoms in the iron bar. This distance between the atoms of an iron bar that is not under stress, I mean, if I just have a piece of iron somewhere, will always remain the same if I measure the distance with respect to the metric. Now, obviously, the number of atoms here between will not change. And because now the distance grows between the two ends of the bar, it necessarily has to be the case that the distance between the atoms of the bar actually grow. And that really means for the bar that it feels a stress. It's like as if you pull it apart. Of course, this growth will be extremely small for a very long time, because the bar, I mean, let's say you could calculate it by taking here the distance, let's say, of between two atoms in the bar, and then multiplying with the Hubble constant, and then you see how fast this distance grows. And because even if this is a light year, which is of course much longer than the distance between two atoms, this will only be a centimeter if you wait for a second. So if this is really only the distance between two atoms, this will be an enormously small, I mean, the expansion after a few seconds or even after hours will be just so tiny you wouldn't realize it. But let's suppose the Hubble constant was bigger, and it will become bigger. I mean, at least if this model is correct. No, no, sorry, that was the wrong statement. The Hubble constant is, according to this model, will not grow because it's that. But let's suppose that the Hubble constant was bigger. Then it would really mean that things would constantly be torn apart. So yes, the thing would at some point just break. Of course, it doesn't break if you, I mean, it doesn't depend on the length because the growth is uniform everywhere. So if you had it twice, let's say you had another star, an S prime somewhere else, and it would be connected to the Earth with another bar, this bar is not under more stress than this bar because there are also, of course, twice as many atoms, although the bar grows twice as much. So it's really an effect that locally always results in the same growth. Which means that if you really would put the real bar, you would have to wait a very long time until it breaks. But the answer is at the end, it will break.
Okay, thanks a lot for the answer. That was exactly my question.
Okay, you're welcome. And thanks for asking, because that's indeed something one should think about. And it's somehow one of these exciting, let's say, consequences of another exciting consequence of the Einstein field equation, which didn't start from such things. We suddenly see that space somehow grows. Of course, that's also connected to a measurement we are doing, but based on a model and an observation that gives us the Hubble constant, we know that this is really the case. Okay, let me now give you some information about the exam. I mean, all the information will be posted also on Moodle, so you don't miss anything if you're still in the break. But maybe there are also some questions, so this will be an opportunity to ask. As you know, the exam will be a written exam. The current plan is still that it will be an in-presence exam. I'm not sure this plan can be upheld, but that's at the moment the planning assumption from our rector. And you have also, I also told you the date, and maybe what I haven't mentioned so far is that you're allowed to bring a summary to the exam of 10 double-sided pages, which can be anything. You can, if you want, copy it from a book or write it yourself. I would strongly recommend, but this is only a recommendation, that you write them yourself, because while writing a summary, you will really learn a lot. So I think you're much, much better prepared if you yourself decide very carefully what are the things that you want to include in a summary and what are things that you don't. And then you will also find things much more easily. The idea of this summary is that we will, of course, during the exam have calculations, and you may need to apply, let's say, formulas like the ones I just used now for the, let's say, such a thing, for the gamma symbols. And of course, under a stress situation, it may be very hard to reproduce all these indices correctly. So this is certainly something you should put on your summary and make sure you can then just use it from there. We will, of course, in the preparation or in the way the exam is made, also assume you have these basic things. So all the, let's say, basic formulas, and by basic formulas I mean the Einstein field equations, the expression for Levi-Civita, the curvature, and so on, they should be on your summary. So we will not state them on the exam sheet, even though it's not something I would expect you to know by heart. But I expect you to figure out what is important and bring them. Now, for the content of the exam, maybe the best way to explain what you have to expect is just to tell you what I asked the teaching assistants to do. So the teaching assistants are helping me or actually substantially contributing to the preparation of the exam in the following way. Each teaching assistant will essentially re-watch or look into 2 weeks of the lecture. So every teaching assistant has like 2 weeks assigned, and then come up with questions, with sample questions that cover the material treated during these 2 weeks. And this could be material that was treated in the course, but it could also relate to the exercises that were done during that week. And the assistants are, I asked them to make sure that among these questions, there are always some conceptual questions and some maybe calculation questions. A conceptual question could, for example, be something like when you are, let's say, on Earth and have a clock and compare it to a clock that is higher up on a mountain, which of the clocks runs faster? And you should just give a simple reason why, one sentence reasoning, not a calculation. It's just, if you have a good conceptual understanding, you should be able to answer that question and also give the right answer. That's maybe a question you may now think about. And then there could also be, of course, calculations, questions, like we give you a metric and ask you to what is now the corresponding, let's say, geodesic equation, for example. Or, of course, also more physics type questions. We had some in the exercises, like how long does it take you until you reach the singularity when you cross the Schwarzschild horizon? That would be a more calculation type exercise. But I really requested this, and will also myself think about questions which are of this more conceptual nature, where you would essentially have maybe a choice of several answers and have to give a reason why you chose a particular answer. And the way I distributed these weeks among the assistants should make sure that all the material is kind of represented in an equal way. So the exam will not, for example, focus on the, let's say, more physics part at the end or more on the geometry part. It's really equally distributed over the whole lecture. And I think this was partially sometimes a problem with earlier exams, for example, electrodynamics exams, where the students were a bit surprised about the focus. So here I really want to make sure it's representative over the whole course, and I hope this scheme will ensure that. Okay, I think that's just how we are preparing it. And we will also make sure that there are not too many questions. So this time we will not give more questions than we expect you to solve. So you don't need to make a selection. This was an explicit wish of the student association, that they don't like to have these schemes where you have much more questions and then have to find out which ones you want to solve. Yes, otherwise I have nothing. No further current information about the exam. If anything else comes up, I will of course post it on the Moodle page.
May I ask a question about the material?
Yes, sure. Yes.
Specifically, I'm intending on writing the exam only in summer. I was just wondering whether like all the material right now will still be available then, or whether I have to make sure to download it now.
No.
And also in particular, the recordings you put on YouTube, are those going to be staying up indefinitely?
Yeah, yes. I mean, this will depend on the ETH-wide policy, whether they will be on YouTube or on. I mean, the plan currently of ETH is to transfer all these videos to an ETH internal server, but they will for sure be somewhere available and easily accessible. So I'll make sure you have them, so you can count on having all this material available. Actually, the recordings, the plan is to keep them for on a long time scale, even beyond the next summer, for future years or so.
Does this also include the recordings from the exercise classes?
Okay, here, not necessarily for the long term, but I will certainly make sure they will also be kept until the exam in the summer.
Okay, great. Thank you.
You're welcome.
There are some more questions in the chat about the exam.
Yes.
So one question is if on this summary sheet, they should, for example, put stuff like the explicit Christoffel symbols for the Schwarzschild metric, or like.
Yes, yeah, I would put them, 10 pages is a lot, and it's clear. I mean, if you now look at the scheme, we've worked a lot with the Schwarzschild metric. So if you have them ready, that's certainly useful. Yeah, I would certainly do it, yes. I mean, there are not so many such choices, there's not like infinitely many solutions. We essentially looked at the general case, like how do the equations look generically, and then we had essentially the Schwarzschild solution, and now you also have had a little insight into gravitational waves, but otherwise there is not like a large selection of things where you would then have to squeeze in things. So because the Schwarzschild metric has such a big significance, I would certainly do that, yes.
And another question is if this last week is also included in the material that is covered.
Yeah, that's a good question. Actually, I think it's for the, I mean, everything until the end of the discussion of gravitational waves is included. Now, the rest was a bit informal and will be a bit informal, what I'm going to tell you now. And I would say, no, let's not include that. I think this should now be the fun part. Now we talk a bit about the black hole information paradox. Also, the part on cosmology was thought to be an outlook, and that will certainly be, if anything, be a part of a cosmology exam. So let's say the material just ends at the point where we ended the discussion of gravitational waves, which was somewhere in the middle of the Tuesday lecture this week.
And another question is whether students are supposed to also be able to reproduce mathematical derivations or just be able to apply the concepts?
Yes, no, I will also maybe ask, for example, what does, let's say, I mean, we had seen the Levi-Civita connection, just to give an example, and then we said, okay, the Levi-Civita connection is somehow one particular connection which has certain nice or particular properties. It should be torsion-free, and it should be such that the metric is invariant. And then you should, for example, be able to show how you now derive the expression for the Levi-Civita connection. So essentially the derivations I did in the course you should at least be able to reproduce the idea of it, what was like the assumption, what came out of it. And if, let's say, if you would ask for individual steps, we just say, let's say in a derivation we had used that and derived this, how would you do that? So yes, you should be able to essentially reproduce these things. I think when you go back through the lectures, my expectation is that if you maybe even watch things now at twice of the speed, which you can do with YouTube, you will find most parts with it in the beginning quite simple, and you will see, okay, these are all things that maybe contributed to your conceptual understanding, but as a mathematical proof, they're not too hard. So therefore, I would expect that you can do that. So at least those things that were explained in the lecture. Are there other questions?
If the students from the University of Zurich will also have access to.
Yes, I will make sure you all have access to the material. Yes. If there is at any point a problem, just write me an email and I will solve it. I mean, that's clearly something I'm responsible for. I will make sure until the summer, until you have the exam, everyone who participated in the course has access to all the material. Okay, are there any other questions related to the exam? Okay. I will maybe in the meantime already write the title of this maybe last more informal part, the black hole information paradox. And if there are no questions, I'll just start with that. So what's this paradox about? So the obvious question that arises in physics is whether general relativity, which is a classical theory, can somehow be reconciled with quantum theory. And this was actually something that worked very well for other classical theories. When quantum mechanics was invented, people managed to somehow quantize electrodynamics. They were also able to essentially understand how other forces in nature, like the weak and strong force, would be embedded into quantum physics. Of course, there we didn't have really a classical version, but the problem of quantizing gravity is so far unsolved. So we cannot regard gravity as a quantum theory. So this has several implications. You know, in quantum mechanics, an object can be in a superposition between two places. But that, if you would now have a quantum gravity theory, you would somehow expect that this would mean that the geometry of space-time is itself in a superposition where the mass is here or there. And it's even unclear what that means, to have a geometry which is in superposition. So we are far away from having a good theory of quantum gravity, but we had so many obstacles encountered that people started to ask whether there are even fundamental problems. Maybe it cannot be the case that gravity and quantum theory fit together. Maybe one of them has to change, or there is something that is even very different and just includes these two things as special cases in certain limits. And in order to decide that, so in order to decide whether two theories can be combined, what one can do is to somehow just look at certain thought experiments where you can make derivations without already having the theory, but just from certain principles that are valid in the individual theories. So for example, in relativity theory, we have the principle, we have the equivalence principle, which I mentioned several times, which means that things should essentially be independent of coordinate systems at the end. And in quantum mechanics, we have another principle, which is unitary time evolution. So you know that any quantum system evolves according to the Schrödinger equation. It can be a very complicated system, but at the end, it's unitary. And the question is, does this unitarity of quantum mechanics somehow lead to contradictions when we combine it with principles of general relativity, including the equivalence principle and the fact that there are black holes with singularities and so on. Now, the black hole information paradox is one particular such thought experiment where people actually found out that there are difficulties, but there's not only one version of this paradox. Now, I will, there are actually two versions I could explain. I will now focus on one given time, actually on the much more interesting one. The other one is for many not really seen as a paradox. So just to mention it. So, or maybe I'll mention the two versions once I've said one more thing, which you need to know urgently in order to even be able to see what this is all going to be about. So remember that a black hole can be represented in terms of a Penrose diagram. And maybe I'll draw one here. So this Penrose diagram looks like this. This orange line is the event horizon. And then we have also an outer region. This point here is the point at spatial infinity. This is the infinite future outside of the black hole. This is the black hole singularity. And this is the infinite past. Remember also that we looked at observers who can move in this space-time. For example, an Alice who falls into the black hole and reaches the singularity, and the Bob who somehow decides to stay out and stays in the outside world forever. And this is he ends at the infinite time-like future. And so far, this is just classical gravity. Now, people started to ask the question, what if we add quantum mechanics to it, but only we don't yet quantize gravity. We just add quantum mechanics on this, let's say, back on this classical geometric background, which is now curved. So this is a much more harmless thing. We are not attempting in the first place to say the whole space-time is itself a quantum object. We're just saying, okay, the space-time is there, it's no longer flat. But on this space-time, we can still put our normal fields that we understand, electromagnetic fields and so on, and quantize them. And that process is relatively well understood. So it's relatively well understood what it means to quantize or to have quantum fields on a curved space-time. So what does it mean? Or what does it lead to? remember that when we discussed all these different manifolds and black holes, we were usually going to a chart. And let's suppose we go here to a chart, which is maybe a useful chart for Alice as she falls into the black hole. Remember, because Alice falls freely, she would typically be in a chart which is which corresponds to her freely falling reference frame. And in this chart, this is also a normal chart. So remember that for a freely falling Alice, being at the event horizon doesn't mean anything special. It's just, of course, that's bad enough. It's a point of no return, but locally, nothing happens to her. Locally, things look essentially flat. So in her, okay, that would be the chart of Alice. Let's make the chart of Alice, let's color code it in blue. And Alice in her own chart is just, of course, a line. And the orange line, at some point, she crosses the event horizon. So in her chart, the event horizon is somehow a line that she crosses at some point. Now, let's ask ourselves, or okay, maybe I'll now make another comment about quantum fields. So as I said, it's relatively well understood how to put quantum fields on a curved space-time. But you have to notice one thing in quantum field theory. I'm not sure how familiar you are with quantum field theory, but probably you're aware of the fact that the vacuum field is not a trivial field. The vacuum field is just defined as the lowest energy configuration. So you have a certain configuration and a certain background, and you just look at the solution which has the lowest energy. That defines what the vacuum solution is. This lowest energy solution doesn't mean that there is somehow it's just a flat wave function. It can be a non-trivial object, and we know from quantum field theory that the vacuum is in that sense not empty. It's just, as I said, defined as the lowest energy. Now, because energy is itself an observer-dependent notion, remember that energy was just one component of the energy momentum tensor. It's not a priori clear whether different observers would agree on the question of what is actually the lowest energy. So they wouldn't agree on what is the vacuum solution. But remember also that we said that ordinary physics, or if according to the equivalence principle, if you are in a freely falling lab, everything should be as if we were just far away from a gravitational field. And of course, we understand how a vacuum solution looks like far away from a gravitational field. That's just whatever it is. It's the well understood vacuum solution of flat space-time. And according to the equivalence principle, this has also to be the solution for Alice. So if Alice has, let's suppose she has a little box with a vacuum inside, so with nothing inside from her perspective, she has somehow a solution. I indicate this with some waves. So this would be the wave functions at any time, which according to her are the vacuum state. Now let's look at the same situation from another coordinate system point of view, from a coordinate system that is maybe appropriate for Bob. So Bob would typically, of course, not have a coordinate system that includes the event horizon. Remember that in the Schwarzschild coordinates, the event horizon is kind of the boundary of the coordinate system. And the coordinate system for Bob, the green one, would maybe look like this. Here is somewhere the boundary of, so you see it's already quite different in terms of whether it's how it's directed, this boundary, but the black hole for Bob is at a certain place. So it's a line like that. And he himself stays outside. So his own world line in his coordinates are like this. Now we could ask, and of course he also sees, maybe I should add that he also sees Alice, but for him, remember, Alice will just smoothly approach the horizon but never pass. This is, I mean, you probably understand that already well, because course, Bob's frame only covers the part until this region. So it doesn't mean that Alice doesn't actually pass. It just means that for in Bob's natural coordinate system, the coordinates are such that Alice never passes the event horizon. Now, remember that when we had charts, we had usually a chart function x, and here we have another chart function from Bob. Let's call it x tilde. And let's suppose that whatever Alice calls the ground state or the vacuum state is called phi. Now, the same state could be represented in Bob's lab. So whatever is for Alice a vacuum state, we could ask, how does it look like in Bob's coordinates? So we could apply the chart transition map to whatever Alice considered to be a ground state, what she thinks is in her box and what is in her box according to her description. But this chart transition map will be such that this state, of course, looks generally very different. Maybe it's a much more violently vibrating state. So this would be, let's say, the picture of the chart transition map. Should have a -1 here of the vacuum state, of what Alice considers the vacuum state. Now for Bob, this is maybe not what he would consider a vacuum state. So from his viewpoint, he would say, what Alice has here is actually by far not a vacuum state. And he could even do calculations and see what happens if the state that Alice has now propagates to him, and he would maybe come to the conclusion that he would measure that this is not a vacuum. So the point is that if we look at a certain region here, let's say this region here, which is covered by both coordinate systems, I should draw it a bit more precisely. So this region is covered by both coordinate systems, and in this region, Alice has a vacuum, and this is maybe the region here corresponding to this. Then this is not a vacuum for Bob necessarily. So that's the first thing to notice, that what we usually consider a vacuum is not a vacuum for another person. But not being a vacuum for that person means that he could potentially detect things. So this radiation, there is radiation from his viewpoint that will reach him. And he could detect that radiation. Okay, that sounds now, I mean, now you see, I'm already combining two theories. I'm now using concepts from quantum field theory that a vacuum is a state defined in terms of energy and that this is observer dependent. And then we have these chart transition maps, and we know that there is something coming out, and we cannot expect that something that looks like lowest energy here will still look like lowest energy here. So the conclusion of that is that from Bob's point of view, if Alice has a kind of vacuum with her, a vacuumized box, it would look for Bob as if there was something inside that would radiate. Now, all this argument that I presented now on a very informal level can be made in a quantitative manner. And there are several people who did it in a quantitative manner. And the first of them was Hawking, and that's why this radiation that I mentioned that Bob would see is called the Hawking radiation. So Hawking found out that indeed when you do the calculation and make this chart transition and then see how this propagates, now in Bob's case, you would find out that this is not a vacuum state, it's something that has a certain temperature in terms of, something that's not a vacuum usually has a temperature. Hawking was also able, by the way, to even determine that temperature, and the temperature of the radiation that he determined was an expression like this in units where all the constants are equal to 1, C and G, and also the Boltzmann constant. So this means that the larger a black hole is, the smaller is its radiation, which is actually to be expected because you know that the event horizon of a big black hole looks much less threatful than one of a small black hole. So we can somehow expect that if you do this coordinate transformation and the black hole is big, this is leading to a less violent thing here than if you do it for a small black hole. anyway, one can do these calculations, and at the end, that's the conclusion. Now, of course, the calculation is based on several assumptions which are not completely, let's say, this is not on solid grounds completely, because first of all, we don't really know whether the equivalence principle can be applied in that particular way. That was just an assumption. We just took that principle. And also, there's another question that comes out. You could say, isn't there a symmetry? Couldn't we say that we first take Bob's perspective and we say, actually, the real state that is there is a state that from Bob's perspective looks like a vacuum state. And then we would come to the conclusion that if we transform this state back, we would see that for Alice, this is not a vacuum state. So the argument I gave so far would just say either, maybe both don't see a vacuum state, but if one of them, Alice sees one, then Bob will generally not say that this is a vacuum state and vice versa. But why should it be that for Alice it's a vacuum state and for Bob it's not? And this is indeed from the argument I presented so far not clear. It wouldn't come out of this argument. You could equally well argue that Alice would see a radiation because Bob is the real person and he defines what is a vacuum, and we first start from there. So why were we allowed to start from Alice? Now, what you have to do in order to come to the conclusion that you can really take Alice as the real observer is you have to additionally make certain assumptions about boundary conditions. So somehow, this was an eternal black hole that I drew here, but I will now, for the remaining part of the argument, move to a black hole that forms. So this is a black hole that didn't always exist. And then it's kind of reasonable if we are in a situation where the black hole didn't always exist, which we assume is kind of a realistic situation, that there was no radiation before the black hole was created. That's very reasonable. Why should there be radiation from a black hole that doesn't yet exist? And now you can see that this means that we have a boundary condition that, let's say, if Alice starts here with her trajectory towards the black hole, which would now only form, then she clearly could prepare a box without any radiation and just freely fall. And during this free fall, there shouldn't, because it's a free fall, there shouldn't suddenly radiation be created, because that would then just mean that the equivalence principle is violated. Alice is freely falling, so it cannot be that she could locally detect that she's approaching a black hole by just measuring and see a vacuum suddenly turns into a non-vacuum. Okay, so that's one thing, but Bob couldn't do the same, because Bob is, in order to stay outside, clearly has to accelerate. And if you have to accelerate, and if you have a box with you that initially was in a vacuum state, it's not at all clear that it remains in a vacuum state, because by accelerating, you're of course enforcing, you're putting force onto the box. And so there, one can even show that by accelerating, by having an accelerated box, you create particles. So the conclusion of the argument so far is, first of all, we saw that if for Alice something is a vacuum state, namely the part of the world where she falls in, where she crosses the horizon, then it's not the case for Bob. And Bob could even then detect potentially this radiation, because of course that's then radiation for him. A non-vacuum state means there are real particles, for him, particles around, and these particles, according to his calculation, would travel towards him and so on, and he could detect them. So under the assumption that Alice has a vacuum state, it's not for Bob, it's a detectable radiation. And together with the boundary condition that says that Alice is really the reference here, because she connects kind of to the infinite past where there was indeed a vacuum and she was just freely falling, we can safely assume that the real state that is there is really a vacuum state. And so that's what led to Hawking's conclusion that black holes radiate. So that's the first thing you have to know. Now I said there are two versions of the paradox, and I want to only mention one of them. However, let's say just to give you an idea of the first version, which I'm not going to discuss. Of course, if black holes radiate, they lose energy. That has to be the case just for energy conservation regions. And so if you don't feed the black hole with more material, with dust and so on, it will eventually just have radiated away. And actually what will happen during the radiation, it will become smaller and smaller. So its temperature will increase. This is very untypical for a thermodynamical object. So it's a thermodynamical object which, as it loses energy, heats up. But it becomes smaller and smaller, and the smaller it becomes, the hotter it will get, and at the end it will be an infinitely hot thing and just explodes in a big crash. But that's something we don't understand, because at some point this mass will be so small that the Schwarzschild horizon is of the order of the Planck scale. And then it's obviously unreasonable to say that we still understand what's going on, because now we are on scales where the equivalence principle can no longer be applied. We cannot do a local experiment if the whole Schwarzschild radius is just of the Planck scale. And so in that sense, it's not understood what happens if a black hole evaporates completely and dissolves into nothing. But the first type of the black hole information paradox is just about that fact. It says that if the black hole completely evaporates, then we could in principle have a huge scattering process in which we create a black hole by sending in matter onto one point. The black hole forms, and then we wait until it completely evaporated, and then nothing should remain. I mean, nothing is there again. So this is as if we did a scattering experiment where in the middle of the experiment, the black hole formed and evaporated. And a scattering experiment described now within quantum mechanics should follow a unitary evolution. Unitary meaning that there's nothing lost. At the end, what you get out is what you sent in. But this obviously contradicts the classical idea that if something passes the event horizon, we will never again have access to it. So that's one part of the paradox. But as I said, that's not a very convincing paradox in the sense that it really goes to it involves this complete evaporation of the black hole where we anyway don't understand the physics. So it's much more interesting to look at the paradox, which apparently just takes place, where the story we are interested in takes place in a regime which we completely understand, or at least think to understand completely. And in order to discuss that, I would like to draw here the formation of a black hole. And maybe you remember that we discussed the formation quite some time ago. So we said if there is an incoming radiation shell, so just have a big shell of radiation that you move into one point, and it's so much radiation that it's so well concentrated that at some point it has it's sufficiently localized that it crosses its own Schwarzschild horizon. And then we found a diagram that looked like this. So the orange line is again the Schwarzschild horizon. The red curve is the world line of the incoming radiation shell. And I could now add again our usual Alice and Bob to the diagram. So let's suppose we have Alice coming from somewhere. Doesn't really matter where exactly she comes from, but let's suppose Alice could in principle even actually cross the horizon before the shell. I mean, that's not so important now, but that could in principle happen. And Bob is a person staying outside. He would end up here. So this is, by the way, the case where we would again say that, or as I said before, Alice comes here from the past infinity. So she comes with a vacuum state, but is always freely falling. So whatever she has in this region here is still a vacuum state. But for Bob, it's not. For Bob, it looks as if it was something radiating. So there's radiation in this direction here. I mean, this is just radiation goes out like light. So Bob will detect radiation as he stays outside of the black hole. So that's now just a picture of a forming black hole. There's no other difference. I just wanted to have a new picture which includes the formation here. Okay, Now the paradox is in principle quite simple to understand if you know one fact from quantum information theory. That's my, of course, research discipline, and there is also a course on this currently given by Joe Renner. And I'm not sure whether some of you even follow that course. I will just now state the result from that course. It's a result that is not completely trivial to derive, so I have to just refer to that course. You have to believe me for the moment that it's true, but it's the result that comes in from information. So the black hole information paradox really is something that comes from information theory combined with relativity, but it's quantum information theory, so it's in some way all at the end coming from quantum mechanics. And the result is the following. So suppose, I mean, these are now the computer science type diagrams where time goes from left to right. So time now goes in this direction. Suppose you create two systems in an entangled state. So I now use certain terms from quantum information, and I just assume you know more or less what it is. And if not, you may look them up and then rewatch that, but I hope you still get the flavor of what's going on. So I have two systems in a maximally entangled state. And I have another system here that I call A. This will be Alice. That's why I call it A. And then let's assume the system S and A together undergo a so-called typical unitary. So it's just some unitary, we don't maybe know which, but the statement is true for almost all unitaries. And this can be made mathematically precise. The space of all unitaries is a space that admits a uniform measure called the Haar measure. And the statement is that if you pick at random a unitary from there, the statement will be true with certainty. So it's true for almost any unitary with a few exceptions that have measure 0. Now let's assume that after the unitary, there's a small system here, or no, there's still something coming out, which I call S prime, and something else coming out, which I call R. Oh, okay, I think I should, yeah. I have not enough space. I'm sorry, I need to move this all a bit over. There's the system S and there's the system A coming in. And now there's, we need to, in quantum information, we measure the size of a system in terms of qubits. So if I say 1 qubit, it just means it's a 2-dimensional space. N qubits, it's a 2 to the n-dimensional Hilbert space. And let's assume that Alice here has R qubits, little r. Okay, actually little r is actually a bad idea because the system R, let me call it Q qubits. And what comes out are R qubits. So because the unitary is typical, it doesn't really matter. I mean, there's some arbitrary unitary, it doesn't matter how I distribute them between the two, because the statement is true for a typical choice of the unitary. You should just think there's some big operation going on, and this postulate from quantum mechanics that everything is unitary comes in via saying that there's some unitary here. And now the statement from quantum information is the following. The statement is that there exists a map which is called a decoding map. So this is again just some operation that you can in principle carry out. And this decoding map takes as input the B system and the R system. And it outputs just an A bar system. And the decoding map has the property that if I just look, how does the whole process here, when I mean, the whole process takes here an input. You see, the A is kind of like an open wire. You can put in here something, and here something comes out. And if we look at this whole process from A to A bar, then this is a identity process, except with a small probability. And the probability is really small. It's 2, I mean, depending on the parameters, it's 2 to the minus r minus q. So it means that if there are a little bit more qubits here in R than are here, then we can assume that this overall map here can be made an identity map. Okay, that's just a statement. Maybe at this point it's completely unclear why this should be useful, but it will become certainly clear in the next 5 minutes. So that's a statement from QIT. Actually, that's already quite an advanced statement. Maybe I call it the statement QIT2. There is also another statement from quantum information theory, which it's a much more basic statement, which is the so-called no cloning principle. And the no cloning principle just says that if I have a system, let's again call it A, there cannot exist a machine such that I get 2 copies out of A, which are both such that in both cases it's the identity. So here the claim is, so this is an arbitrary process P. For no process P, it is true that A to A1 bar and A to A2 bar are identity operations. So in some way I cannot have a quantum mechanical copying machine. If I have here some object, it comes out identically here and also identically here. This is not possible. Okay, that you also have to believe, but that's a statement you may have already proved even in a basic quantum mechanics course. At least I hope, because it's really a very fundamental statement. Okay, now comes my final, let's say, combination of everything that we did. So let's keep this, or let me first copy the diagram. Or yeah, actually I more or less copied. I just need to have a fresh version of it. To have a little bit of space here. Okay, so that's again the singularity that I'm drawing here. And then we have the event horizon here. We have also the, we have Bob. Let's suppose Bob really starts from infinity. And now after some point, he decides to create a mass shell or a radiation shell, which he throws into a certain direction, which then forms a black hole. Okay, I mean, you see this whole experiment is highly unrealistic in practice, because how should we form a black hole? But this is why it's a thought experiment. If physics is consistent, it should even work for situations that are not technologically feasible. So forget about the technological feasibility. Just think of Bob coming in and creating a mass shell. Somehow, maybe he has prepared it, it just executes it at some point, which goes into the whole thing. But he does it in an even more sophisticated matter than you may have thought. It would already be very difficult to create a mass shell, but let's suppose or a radiation shell, or whatever it is. So let's assume it's a radiation shell with many photons that he throws in so that they form a black hole. But let's suppose he also entangles all these photons with some memory he keeps. So he has all these photons that should form a black hole, but at the same time he keeps another system B. It's kind of a quantum memory, a huge quantum computer, which is completely entangled with all the photons that form the black hole. Okay. And then Bob's trajectory somehow continues. Maybe he goes here to see the radiation of the black hole. And at the end, this time, let's say he also wants to meet Alice again. So where is Alice? Let's suppose Alice starts the journey with Bob. And then Alice here from this point on, once the mass shell is created, and this could also be earlier. This actually doesn't have to be here, but let's just, it doesn't matter. Alice goes in, but then she tries to make sure she can still meet Bob before they both hit the singularity. Of course, this should not be steeper than 45 degrees, otherwise the Penrose diagram wouldn't be valid. Now there is also radiation. I call this R. Let's now, for simplicity, assume that Alice just takes one qubit with her, which I call A. Okay, and now comes the big combination. If we now assume that from Bob's perspective, everything is unitary, or I mean, if quantum mechanics was true, then it must necessarily be the case that if you ask Bob what happens here in this region, in this yellow marked region, when Alice, excuse me, that's not exactly here. It's a region where somehow Alice, from his point of view, is already further inside than the point where the radiation comes from. And now, from Bob's point of view, this could be a, so I put Alice here. This should be, at the end, every process should be unitary. So in particular, also this process. So now compare it to this diagram. So let's suppose this yellow region that I've drew here is at the end a unitary, a typical unitary. What goes into this region? Maybe I should here put the radiation a bit differently. I'm only interested in the radiation from the point on where Alice crossed. I mean, that comes after Alice. So what goes into this whole thing? So that's a huge process for Bob. So first of all, into the process goes S, all the photons that form the black hole. Also Alice enters the process, and what he gets out from the process is radiation. And of course, he keeps this memory. Now, this is exactly the situation here. So the yellow part just corresponds now to the unitary. So we just selected the unitary to be now a model for this part of the universe. I mean, everywhere, everything should always be unitary. So in particular, also this part of the universe. And you see the connections are exactly like this. Here is S and A going in, S and A going in. S prime doesn't, I mean, goes out, but somehow you could think of S prime as being at the end inside the black hole. So this is maybe coming out, but this is not accessible for Bob. But R is again accessible for Bob, and B is something he kept anyway. So according to this quantum information theoretic result, Bob could now put here a decoder and reconstruct A bar. So in other words, Bob has now a copy of Alice. It's just qubit. I mean, not of the whole Alice, but okay, the idea was Alice takes a qubit inside the black hole. As she falls, there is radiation. Bob decodes the radiation and gets a copy of the qubit back. But of course, from Alice's point of view, as she crosses the horizon, nothing happens. So she's still there as Alice, and she will now try to meet Bob. But when they meet, they would encounter a contradiction to the no-cloning theorem, because now Alice and Bob meet again, and Alice could say, look, here is my qubit. And Bob could say, oh, but I have a copy of it. And this now contradicts the no-cloning principle. So that's the paradox. Okay, that was probably a bit fast, and maybe it's useful if you just rewatch this at half or twice the speed or whatever. But this is really the essence of that version. There are several versions of the paradox, but that was one that heavily relies on a quantum information theoretic result. And you see, we haven't used any details. All we have used, I mean, we have not used details of how you could make quantum gravity. We have just used the fact that we assume that if there is a quantum gravity theory, quantum mechanics should still be valid, and therefore all evolution should be unitary, which came in here. And then we assumed that there is radiation that can be detected again by Bob, and this is just part of what comes out of the unitary. And then from quantum information, we know that this would lead, and this would enable Bob to get a bar back, and then we violate the no cloning. So we have a contradiction to known principles from relativity theory and quantum mechanics, which really implies that in order to build, on the way to build a theory of quantum gravity, we have to learn to deal with these things. There has been a lot of progress recently in research on that, and that would be, of course, a known lecture to discuss all that. But this is in some way the starting point of an extremely exciting research direction where we are trying to find hints of how a future theory of quantum gravity could look like. Okay, I think this ends the course on general relativity with this outlook on future research, both in cosmology and quantum information, quantum gravity. I hope you enjoyed it, and I hope also to see you again in one of the future lectures on whatever topic.